for today's America Makes TRX webinar. This particular webinar is on simulating and optimizing additive manufacturing process using AlphaSTAR's GENOA 3DP product. A little bit about the TRX series. In fulfilling the America Makes mission to expand the footprint of additive manufacturing and 3D printing in the U.S., we have put together this America Makes technical, what we call the Technical Review and Exchange webinar series, or TRX webinars. And this platform enables the 3D printing community to share knowledge and discoveries with a broader audience than they may have been able to reach on their own. Just a brief note about our protocol here and procedures. At the end of the presentation today, we will have an opportunity for Q&A. If during the presentation you want to submit questions in the Q&A space on your WebEx screen, please do so. That way you can you may not lose your train of thought as we go through this presentation. So if there's any issues with that, but just put your questions into there, and then we'll do our best to answer them all at the end of the presentation today. So today I'd like to introduce you to our speaker, our presenter, Mr. Cody Godinez. He's a senior structural engineer at AlphaSTAR. A little bit of background from him: prior to working with AlphaSTAR, he worked at Lockheed Martin and for NASA at the Johnson Space Center. So I'm going to leave it to Cody at this point to take you through this presentation, and welcome everyone on board. Go ahead, Cody.
Thank you very much. Go ahead and go next time. Okay. So thank you everyone for joining. Today we have an agenda set up to talk about the simulation and optimization of the additive manufacturing process with GENOA 3D printing. We have some slides on background showing the challenges in additive manufacturing, and they are separated into categories. There's material modeling challenges, process modeling, as well as continuation from those simulations onto service loads. That's the whole discussion. Another one of the things that we want to address is why you'd want to use GENOA 3D printing in the simulation process. What makes it different from everyone else? Our two approaches that we have are big area additive manufacturing, otherwise known as BAM, and fused deposition modeling, FDM. We talk about the simulation process as a whole and then go through 3 video demonstrations, one in which we print up a 3D Strati car using our 3D printed module. So we take in a G code, we show the settings, we print it up. Another video demonstration is the Thermo simulation of an isogrid model. We already have the G code, we've done the simulation, and we're showing the laying down of the material and the temperature contours. The last demonstration is on our MCQ, which stands for Material Characterization and Qualification. We're showing ABS CF13 material. We show the inputs, the types of how you enter the mixing of the materials between the chopped fibers and the matrix, some of the assumptions we have, and the results that you get, as well as the module that we have for determining through the thickness angles and thicknesses of your chopped material. And finally, we finish up with case studies using the material characterization for both unfilled and filled materials for ABS system and ULTEM 1010. And we finish up with some more interesting case studies for AM simulation with actual parts. One is a Bosch part, is a multi-hull component. And finally, we also have a multi-material isogrid simulation. Both of them are validated with tests. The Bosch part, we're looking at defect detections. We show load displacement. And the isogrid material, we also show load displacement, and we show a little bit more about the printing simulation. Both of them show defects after printing, residual stresses and damages that eventually affect the service loading conditions. And we'll finish up with some Q&A. Some of the problems that we have when printing thermoplastics is that the loading induces residual stresses. Now you have the mixing of the materials, you have materials within each layer, the carbon and the epoxy and the thermoplastic, and then as beads of materials are laid down, you have temperature differences across the layers, and so there's a temperature difference which produces asymmetric shrinking, bending moments, and it lends itself to produce cracks within the beads and between the beads. which is shown on the bottom of the two pictures on the bottom. Some of the printing process that we see are shown with two videos on the top. One shows the printing process, and then when we do thermography, we actually see the heat-affected zone, and eventually those cool off. We've done validation cases with the thermal drop-offs with several materials with our software, and that leads into the residual stresses, which eventually leads to cracks. For multi-materials, they can be separated into two categories. For example, for thermoplastic, but either way, the materials model should consider defects in the as-built and printed parts. For thermoplastics, you do have high porosity, and sometimes there's non-optimal layer or poly-to-filler interfacial bonding. This produces residual stresses, delaminations, and wrinkles. We also get defects, fiber waviness, and agglomeration. These kind of artifacts are seen in the bottom three pictures, which the bottom left shows some of the interfacial bonding, the debonding between the filler and the matrix. And then the middle picture shows delamination between the layers. And the right picture is a odd-shaped type of porosity and hourglassing that's formed between these type of beads. This is actually the Ultem 1010 material. So you're never going to know what you're going to get in different regions and throughout as a material as a whole with 3D printing. On the right, we're talking about multifunctional material problems. Well, you do have gas and process-induced porosity, unfused powder melting, the joining from metal to PMCs has different regions, and any dissimilar materials has kind of debonding effects. Okay, and it lends itself. On the bottom pictures, we show that gas and porosity are different on different regions of the model. And on the right-hand side, we show the right-hand side should have been a full grid of titanium to PMC bonding, but you see on the top, it's showing the underside, the titanium is not fully bonded. And these were sort of Latin hypercube studies on speed and power. So what we're trying to say is that the whole process lends itself to, and this is where simulation can help out, is that speed, power, and other printing parameters need to be optimized. Why do you want to use GENOA 3D printing environment? Well, you do want to design AM components with improvements in mass, cost, schedule, and performance. Let's look at the different categories of how it can benefit. For the material models, we have full prediction of mechanical and fracture properties and usage within the simulation as a function of temperature. We can predict the tensor orientations through the thickness, which means that we can determine fiber angles and thicknesses throughout your chopped material. For process simulation of the AM part design, you want to reduce the following inherent as-built items: residual stresses, distortions, voids, shapes, sizes, and distributions, printing pattern anomalies like bald spots, they want to be identified, and reduce the amount of damage and fracture. Your as-built part will have all of the above. The point is that you need the software to tell you how much you have and what you can do to change it. Finally, you need to be able to move with those as-built items into service loading simulations for the as-built part to assess its performance and change any of the above items that we just mentioned. So the whole software suite lends itself to identify root cause problems due to manufacturing process parameters and determine scatter and uncertainty and sensitivities to material, process, and load. Every one of these items, these capabilities, helps reduce the amount of testing needed to be done to build a good AM part. The beginning of this software began with this VAM project showing on the right-hand side, Big Area Additive Manufacturing with Oak Ridge National Laboratory. They printed a Strati car, and we simulated it. Each took under 24 hours. Eventually, we got the simulation down to 12 hours for the full Strati car model. We looked at the tool path, we looked at bald spots, we showed delamination, residual stresses, and it built up our software with this test-validated case. This led us to get the 2015 R&D 100 winner award for this 3D printed software. We came out in the Detroit Auto Show the following year, And so here we have our AlphaSTAR banner, and then it's kind of the epitome of what 3D printing can do. We're showing the Shelby Cobra that the whole car was 3D printed and assembled. The 3D printing, again, takes a day. Painting takes a week. So everything was assembled within 2 weeks, ready for the car show. The flow process that we take. This is a summary of everything leading up to those kind of predictions. Now, one thing to note is the car is a BAM process. So it's a big volume, and we're doing layer by layer detail simulations. The other process is when you're following the printing path more precisely. It's reserved for smaller models. Those are the two different approaches, BAM and FDM. Now, the flow process is the first thing you have to have is a CAD model, which you turn into a G-code. There's many softwares that can do that. So you have your G-code file, or you can, we work with several different G-codes, and you generate your mesh. In parallel to that, before or during or after, you have to do your multi-scale material characterization. This material model must predict temperature dependency on mechanical and thermal and fracture properties. For composite materials, you must consider fiber orientation, constituents, curing parameters, and the effects of defects. For powder metal, you must represent it with creep diffusion, void growth, surface roughness, and oxidation. These two, the mesh and the material model, are combined, and the user gets to choose the solution type. In the beginning, they want to know about the temperature distribution, so they perform an uncoupled heat transfer analysis. That's all it is. You get the knowledge of the temperatures. That information is saved. Okay. Another solution type, the next step that they would do is to perform a sequentially coupled solution. So the user can assume a temperature drop down on the beads if they know that beforehand, and the solution tends to run faster. The epitome of the solution that the user gets to choose is a coupled thermal structural analysis, in which the structural analysis uses the heat transfer results, and they discuss back and forth to give the full solution throughout the simulation. This leads to model predictions like residual stresses, delamination initiation and propagation, and finally all the damages that you can get from the simulation. So on the bottom, the red areas are damage areas, and we'll zoom into this box in a later slide. It shows all the damage mechanisms and the damage types in the fiber, in the matrix, across the beads, interlaminar shear, measures of delaminations. These initial simulations can be carried forward to scatter and uncertainty analysis, probabilistic assessments, which also gives you the sensitivities of the material, manufacturing, and loading conditions. They give you the sensitivities of the amount of damage that you have, or the strength of the material, strength of the structure in service to those variables. This path to prediction. Now that was our flow chart. Here we're actually showing a test-validated case that we have a journal publication for with Oak Ridge National Laboratory. Again, you begin with the material characterization. You do coupon testings. These are what the coupons look like. You break them. You break a few of them. You know the stiffness and the strength for different flows. Here's the 0 degree, here's the 90-degree flow, stiffness and strength. So that forms your chopped material model. You're able to reverse engineer every fiber property that you need, all the matrix properties, and all the nonlinearity. The validation can take the form of a thermal model. It can take the form of a bending model. Here we have the thermal model that was validated, showing the dots show test curves. So we're showing the temperature drop-off over time. The solid line is our simulation of a wall model. So we printed the wall model with the predicted mechanical and thermal properties and matched the test that they measured. There's many ways to measure the temperatures of the part as they're being printed, but here is the cool down. And so that produces, once you have that validation, you can use that in bigger models with confidence that you're going to get the right residual stresses. On the right-hand side for that wall model, we're showing a short video of the damages that are springing up within the wall. Okay, and it's difficult to see. Again, in other slides we have a little bit bigger picture, but we're showing that damage mechanisms like fiber failure, delamination type of mechanisms, different types, fiber crushing, they're all contributing to the strength of the part. The red zones are showing where they pick it up. And we can select individual ones, and the red zones will turn on and off, identifying regions for individual damage mechanisms. In addition, we have the percent contribution. We know that of the total volume, what percent is due to one specific damage mechanism. You do not see this in any other software out there at this moment, and we've been doing this for 20 years. Finally, at the bottom, we are showing the actual part. So we move on to the structural level. This is the test of the Strati car. We're showing the additive manufacturing build delaminations, and they can get quite severe. You don't want to print something this big over and over again. Software can help decide what to do with the process. And we've done this for multiple times using our software, validated cases in which we reduce the residual stresses and the damages before the printing. In the middle, we're showing the predictions of all the delaminations. So we show the mesh at the beginning, and then as the part is being built, there's a lot of micro cracks. Okay, these lead to macroscopic failure. On the right-hand side, we're showing the best of our predictions of thermal, and then this can be coupled with a structural analysis. We call this a dynamic moving grid analysis, and it models, this technique, this approach models the FDM process. So as you can see, we're actually getting into more detail. We're not seeking results layer by layer, but now we're following the beads path more precisely. This will increase your CPU time, but it allows you to capture things. I'm going to trace this line over here, wait for the heat buildup. I'll tell you when to look for it. So the red zones right over here in this region, you're going to see trapped heat right here. This is what you don't want, because when the next material comes around, this temperature difference and the trapped heat leads to delaminations. And so as far as the computational platform, the part one is model generation. You can visualize your bald spots, look at your printer path lines, look at all your layer times, your material orientations, which leads up to the simulation model. The simulation model includes convection, conduction, radiation, temperature-dependent cohesive failure, and material models between and within the beads, and allows the user to do thermal or coupled structural thermal solutions. Part two is the simulation. As I said before, you can determine all your residual stresses, your deformations, whether they're permanent or temporary during the print, your damage mechanisms like interlaminar shear and delaminations highlighted over here in red. Finally, we get to see what this table is all about. As you can see, we see the percent contribution and the damage type. And for those with a little engineering knowledge, we know that S11T, the one direction is when the fibers are being pulled, two direction is matrix, three is also matrix, depending on the orientation of the fibers. So we have measures of delamination highlighted in red and showing over here on the model. So this model, like I said, took 12-hour CPU times, 24 processors, and it's a multi-scale material model. Some of the highlights of the delamination. So in addition to seeing what you have here globally in the center, you can zoom into a certain region and identify, you can quantify the warpage and the delamination between the layers. You know, on the top right, you're actually seeing that they actually are separating. So the details that you can get from such a model is immense. Finally, we have a video of our GENOA 3D printing module. I'm going to go ahead and play it. We begin with some material properties, and then we go into the mesh generator, which is the actual 3D printed module. The user is able to choose the G-code format, ORNL, RepRat, as well as an experimental format, import the G-code. Just want to note that the video is edited to make it shorter, just when we do things like select the directory. And then it's going to bring in all the information, which includes the layer information, the extent of the model, the up and down of the G-code, and then in our little dialog box over here, the user's able to enter the types of mesh that they want, further down the bead width, whether or not they want plate support, temperature boundary conditions, the output interval in the simulations, if they want to convert time or length, gap conductivities, convection coefficients, emissivity, mode 1, mode 2 fracture, and then they generate the model to preview it. This is before exporting the actual simulation model. The actual generation takes about 2 minutes. It was a quick edit to get it in quick. It takes about 2 minutes, and we see that the model is generated. Now we can look at some of the characteristics. I'm going to turn on the angles, so we're looking at material orientations, showing the print angles, and now we show the deposition time. And then finally, if we want to look at printer path information, we have to study one layer because it would be too involved. So I'm going to choose layer 10 at this point in the video and say, show me my printer path lines. Well, what do I got to know about this? Remember, I pre-selected a certain mesh density, which I can change. So it's showing you layer number 10. Zooming into a certain region, near the back side of the model. Now again, once you choose a mesh density, the higher density, the higher CPU time you're going to have, the more file space you're going to need. So I'm increasing it by a factor of 2, and we can see that we're going to capture more of the printer path curvature that we have. Okay, so we get a little bit more details. And then I'm going to go into another region and then show that, we have the printer path and the bead width entered in this module. Now, if I increase the density a little bit more, I can see that the printer path and the bead width is going to skip a certain region. So here I have, I'm going back in the density, and I'm going to increase it a little bit more just to do some checks in different regions, and some bald spots are going to appear. So that you're skipping a little bit of regions, you already have some bald spots in your printing in that layer, so it's something to address either by path or another machine setting. Now, the user can choose the type of analysis: uncoupled, coupled, sequentially coupled, fully coupled, thermostructural, the type of additive method, whether it's BAM, so that they want to solve the solution layer by layer for big models, or go ahead and choose the amount of lumped elements and choose this FDM approach. So down here on the bottom, we're going to scroll down a little bit on the dialog box, and we get to choose what's known as lumped elements. How many elements do you want to trace along the G-code before you solve the thermostructural solution? Now, you cannot go one by one unless it's a small model. So you need to be, are you going to do a quarter layer, a 10% of the layer, things like that. Those are the decisions that the user can make. Now, the next video that we have is showing an isogrid model that we're showing later on. And so now I'm showing the FDM approach, or the dynamic moving grid, and I have a chunk size that looks about 20 elements. And the red elements are being solved for, the rest of the model is being cooled down. Again, I'm going to skip some of the middle parts of this and go to the isogrid part where the deposition begins. Just wait for the layer to hit the corner. So you have initial base layers, and then you start forming up the details of the print, which in this case, we see the isogrid pattern forming over here. The rest of the part is cooling off over here, which could lead to delaminations. That's what the software is there to tell you about. And, the video goes on with the same kind of print, and this is the first layer pattern for the isogrid, then the pattern keeps on changing, a little bit different as you go layer by layer. I'm going to move to the next demonstration video. This is our MCQ chop, so it forms the background of all the material modeling. So we do have a database of libraries and examples. They're all test validated. When the user opens up one of the projects, you can see there's a series of instructions defining quick steps, a little bit about the printing. Anything that we have, references, test curves, are all going to be defined. Over here, we are showing in the project inputs that comes into the project the AS4 particles, all the properties, strength, interface strengths, the ABS properties, and then finally over here a little bit about the chopped composites, which tells us that we're choosing a certain fiber, that whether it's straight or wavy, the weight ratio, whether or not we have interface effects. And here we're showing our damage and failure criteria to be strength-based, and one interaction we can also choose strain-based. So now when I run chopped mechanics over here, I'm actually by default analyzing one layer with that type of information. And I can see whether or not I have aligned, I'm going to move to my modulus properties, whether or not I have an aligned orthotropic or transversely isotropic material, or a 3D random, which would be an isotropic material, and I'm predicting strength and stiffness. So I move to strength there. Now I'm showing transverse isotropic strength. Now, if you have test data, like orientation tensors, you use one of our other modules and you enter the orientation tensors, A11, A22, you can also use flow and cross-flow data to determine the layup through the thickness. So now it's reverse engineering all this information, the angles for the thickness, the angles and the thickness all the way through the thickness of your material, and you can export this back into your orientation distribution. Now instead of one layer, I'm going to analyze all these layers right over here. So now they come back into the project. And then I can pull this in one other direction using our progressive failure module in Chopped. So I'm adding the module and then running the analysis, and it's going to show me my stress strain curve. There's other types of modules in here. They do probabilistic. One of them is the one that uses flow and cross-flow data, design failure envelopes. So here's the stress strain curve, and now what I get out here is through the thickness damages of my chopped material. I'm scrolling down on the stress strain curve, and then I'm going to scroll back up and determine where damage initiates, and it initiates with fiber failure in the primarily 0 degrees, and then you lead up to shear failure in the other materials. This concludes our demonstration videos, and now we move forward to our test cases. We start with MCQ. We have two. One is for the AS4, which is scatter and orientation. One for the OTEM 1010 with thermal and chemical shrinkage, two very important effects, always physics-based. So MCQ chops, these are our capabilities. If you had one slide to take with you, this would be it. The top in the green is showing our inputs. Nonlinearity, it's going to be out there in test data. You're going to have manufacturing give you nonlinearity. We take that as an input, or we can reverse engineer it from chopped coupons. Particle shapes, the reinforcements, or void shape sizes, the aspect ratios. As some of the inputs, you should know your approximate shapes, your approximate volume ratio. Manufacturing defects like the void shapes through the thickness, interface effects, agglomeration and fiber waviness. These are all part of the user-selected things that's going to give you your chopped material information. Now, I said before, on the left-hand side, there's two ways to do the MCQ chop. One is using the tensor orientation through the thickness. So this is actually showing test versus MCQ. So you validate your model through the thickness, and you use it also for the nonlinearity. And then also if you have flow and cross-flow coupons, this is showing flow, cross-flow, and then 45-degree coupons cut. You can reverse engineer everything you need, and then, using two, and then predict the next one, which would be a validation step. Then move on towards bending to your bigger models, put it into the 3D printing model, whatever you need to do. And some of the additional outputs is material uncertainty for reliability, your fatigue-like design failure envelopes. It can tell you good regions where you have cutoff, for example, here, depending on the failure criteria. Your mechanical properties, you need to be able to predict stiffness, strength, and conductivity. Okay, even electrical resistivity, all those are becoming important with the NDE and knowing what's going on with the test. We see that more and more. For our AS4 ABS material, we're showing here that we're predicting the scatter and uncertainty and of the modulus, the tensile modulus, and strength for different fiber weight percents, also known as fiber loading. So here we're showing the test versus MCQ, as well as the scatter box and whiskers charts, up and down vertical axis. So we're able to predict both deterministic and the scatter as well. Our inputs were the AS4 properties, the ABS properties. fiber length and weight fraction, the voids, the interface shear strength. We did have the orientation tensors to the thickness, and we were able to do the uncertainty analysis when we use the fiber length as random variables, which would mean that we have the standard deviation over the COV. Now, the saturation is because as you introduce more fibers, then you start to introduce more defects between the fiber and the matrix, as shown here in the bottom charts from 0, 10, 20, 30, just like in over here. And we're showing that, yes, defects do it indeed, but they show up within the material instead of across the beads as shown over here on the left. Now, the orientation tensors were able to predict through the thickness, and we've shown here verified with test, chopped and test, for 10%, 20%, 30%, 40%, using the paper physics and laminate mechanics methodology. For Ultem 1010 material, now this is something to note. Now, when you think of chopped composites, you might think, okay, I just have my thermoplastic and then I have my fiber. No, no. Before that, you have a neat resin as shown here. This is why we call it unfilled. You have a neat resin and you have air particles. And those air particles have a certain shape. In this case, we modeled them as voids. You can change it through the thickness. They will have different shape sizes and orientations as well. And that leads to this neat resin, a neat printed resin. And we're showing here our predictions for all these print directions, X, V, VX, percent differences are shown over here on the table. So we have these validated cases for stiffness and strength for all the directions, out-of-plane directions, in-plane directions. You know, it leads to an anisotropic matrix to begin with. And that can be used further in our micromechanics code. This would be considered nanomechanics. Then you take that matrix and you mix it now with fibers. So you have this matrix with voids, you mix it with fibers, and you fully define your 3D printed chop material. The inputs are shown here on the left, the typical properties, some of the stress strain curves for the fiber and the matrix. And what you get out, again, these are the flow and the cross flow. And then the validation cases, the plus minus 45, and you're ready for full predictive test reduction, cost-saving modes. Like this, allowables, they're very expensive. You need a lot of simulations. Here, what we use as the design variables is some of the manufacturing variables, some of the matrix variables like strength and stiffness. We entered a CO coefficient of variation and distribution type, and we're able to predict the B basis of the ultimate tensile strength, as well as, and showing here, test versus MTQ and the percent difference on the mean and the COV. And so we're able to predict the B basis. And we're able to predict, and in the same simulation, get out the CDF, which can be used for reliabilities. And the sensitivity is shown over here between all those variables. So we're saying that, okay, the matrix stiffness, matrix tensile strength, and the fiber length have importance on the ultimate tensile strength. It gives you your focus for your manufacturing, for your design. Now, temperature dependency is extremely important. We have a multi-factor technique to calculate temperature-dependent modulus, Poisson's ratio, and strength, as well as which leads up to the specific failure types at different temperatures. So here we're showing all the curves, temperature-dependent modulus for what I just mentioned, as well as the ply damages. This is showing for room temperatures. And you might see a switch. If you have different orientations through the thickness because of your chop material, you'll see a switch in damage mechanisms at one temperature to another temperature. And that's what the software allows you to study. And we get into our more interesting studies, which is the structural. We're moving past the material for those who are interested now in the structural. This is a Bosch test article. It's a multi-hold part. It's a very interesting test article, from small squares to big squares at the top, small circles at the bottom, and they're pulling it in tension, and you can see a fracture path. That was actually two test articles. Part one, as we mentioned, is the material modeling. We have inputs from data sheets and from figures on certain articles and nonlinearity. So everything is shown here in the charts. The assumption is that there's voids, about 22%. The voids are cylindrical with an aspect ratio of 4. And we're able to predict all the necessary properties, compare them with tests, and move forward into the structural model. Now, for the printing process simulation, on the edges between the holes and the part, there's a little printer path change, and it's producing voids. And you can see it within the surface roughness. Again, printed parts. They have surface roughness and they have voids that need to be accounted for. Our 3D printed software did pick up on this. So we mentioned, hey, zone in this area, tell us what's going on in this area. You might have some bald spots because of the printing and the bead width. That's what the software was before. So we detect those. We detect the voids, shape size distribution, which leads to stiffness degradation and fatigue life reduction. Okay, and one thing to note is that the material orientations, as shown in the video, are being shown. You go in there and you determine what is your orientation in a certain layer, so you can see just in certain regions you might have an orientation that you do not want. Finally, part 3 is the prediction of the service loading. So the service loading was static. We used displacement control, maximum stress-based criteria. We didn't account for residual stress in 3D printing. That's something that's later to be done. This is an ongoing project. And the post-fracture degradation factor was 15%, which degrades the properties after fracture within each layer. And here we're showing the 2 test articles. You can see there's cracks forming, and they lead up to the corners. The 2 test articles tests are shown in blue, and then the simulation is shown here in red. As you can see, we're identifying also the same peak between the simulation and the test articles. And this, when you zoom into the simulation, you're able to determine the locations of damage initiation and then how it propagates from those regions. When we look into that in more detail, we're assessing the types of damages and their location. So damage initiation, primarily it's fiber failure, and we're looking at on the hold part, the circular holes along the edges, perpendicular to the loading. When we look at the damage occurrence in, the order, we see 1, 2, 3, and these 2 happen around the same time, which is a little bit what our prediction is showing when we look at the propagations. So we zoom out in the load history. We're also showing the same critical regions, 1, 2, 3, and then along the edge of the big box, as well as the damage types. So is it fiber failure? Is it matrix shear? And now here we're just showing the delamination damage to be in the center and the top or the side of the specimen along the hold part, the holes, circular holes. Our next case study is an isogrid structure shown here on the bottom, and we're doing service load simulation. We did the FDM simulation, which means that we use the dynamic grid, moving grid approach to model diffuse deposition modeling, which was in our video. So now if we look at a point which is by a wall, but it's on the base, and we look at the thermal history, we can see that we're seeing a lot of the fluctuations, and that's due to the new material being laid down, and as time goes on, the part is printed in the vertical direction, the new hot material is further away, and so this tapers off. FDM is a dynamic moving grid approach. That's what it lends itself to, and this is just showing several slices, one slice at several different times as it's being built up, as we showed in the video. Finally, the residual stresses and the deformations are showing in these 2 charts. They're zoomed in. That allows you to determine warpage, and we can identify regions of critical damages or just micro cracks as well. So you see up in the walls, we're starting to damage due to the print. There didn't seem to be severe damages after the print. And this led us to test the isogrid. Here we're showing the 3-point bending test of the isogrid. And on the right-hand side, this test was performed by the Air Force, so we're not showing the values. But the test curve is shown in black over here, and then the test peaks right over here and then drops down. And then our first blind prediction needs to be a little bit corrected, but our first blind prediction was up here. And then we looked at refining the load steps. We got the blue curve, and then finally we added simplified, more representative contact in the areas, and we're getting the green test. So the problem begins with getting the right micromechanical model, which feeds into this type of model, and you can fully go into the predictive phase. Again, reverse engineer, calibrate flow and cross flow, predict something else like 45, put it into this model, and you're in the predictive phase. then the savings continue as you try to do something like a probabilistic analysis, which determines A and B basis values, the CDF is shown on the bottom, as well as sensitivities. So I'm I'm numbering the sensitivities and showing what they are identified with over here. Chamber temperature, fiber strengths, matrix strengths are these two, and print speed and print pattern. As mentioned before, we can change all of those parameters, material, process, loading to determine sensitivities. And we're seeing that some of the top three were sensitive to print speed, matrix strength, and fiber strength and compression. Matrix strength and compression also. And the damage mechanisms during loading are identified also. So we show the overall damage footprint, the damage types, and then we can break it down and highlight what's fiber failure, what's matrix shear, what's matrix tension, and what are the delamination regions. So it fully allows you to identify. In conclusion, for this whole presentation, GENOA 3DP can simulate the entire AM process. The materials can be unfilled and filled, temperature dependent, have the effects of defects, and we do have a validated database. For the print process simulation, we're showing what leads to the next one. You start with the model generation, choose your analysis type, for example, dynamic moving grid, do your predict your heat affected zone, as well as this can lead to global and local modeling. You're able to predict residual stresses, deformation, delaminations, and the locations of damage and fractures. So you have your as-built part, either or, down onto surface loading as well, damages and fractions. The thermal profile model can be validated, as we've shown with the wall model, and this leads up to a couple structural thermal solutions. Now this total package allows you to improve manufacturing process and adjust design parameters like printing speed, intrusion distance, material temperatures, ambient temperatures, material types, inclusion orientations, and aspect ratios. Some of the things that we have, this presentation was for thermoplastics, 3D printing of thermoplastics. We just released that software. The future release plans that we have is for 3D printing of metal powders, which we have already have a database of validated cases, but our release is scheduled for Q4 of 2017, which will include SLS, DMLS, direct laser deposition, electron beam melting, and finally 3D printing of ceramics, which will be in Q1 of 2018, which will account for the binder jet printing process. This concludes the presentation.
All right. Thank you so much, Cody. That's all wonderful information. I don't know if any of our online participants have any questions for you, but if you do, please remember to enter them into the Q&A box text fields there. There are a couple questions that I have here though for you, Cody, if you're good. Is this software capable of calculating shrinkage as a function of temperature?
Yes, it is. We can calculate both chemical and thermal shrinkage, which leads to some of the residual stresses. And you need to have we are able to also predict the temperature-dependent mechanical properties as well.
Okay, excellent. What printing processes are currently supported, and do you have others in development? Can you talk to that?
The currently supported printing process is fused filament fabrication, otherwise known as FFF, FDM, which is Stratasys Systems, RepRap, Farsoon, BAM, and then some of the ones that are not released as mentioned in our last slide, which is SLS, DMLS, which is used by EOS machines, DOD, EBM, which is used by the RCAM machines.
Okay, so we can expect to see some of that then. That's great. Once again, anyone on the call, if you want to contribute any questions. Here's another one though. What is the significance of material modeling when simulating 3D printing process?
during the 3D printing process, the material goes through a temperature range. It's laid down at a high temperature and then cools down. So the most important thing is to be able to predict the temperature-dependent material process. And these are the thermal temperature-dependent processes, the fracture properties, as well as the mechanical properties. Now, you need these properties to be able to, like, also stiffness, strength, conductivities, mechanical fracture, and then these will allow you to fully predict things like a part being service loading, damage evolution, as well as before that, the final printed damage and fracture state of the part. Different parts can exhibit delamination after printing, fracture after printing. There's big difference between a good part and a bad part, and that's why you need simulation to prevent wasted material.
Okay.
And man time for printing.
Sure, sure. Well, is the technology capable of simulating additive of continuous fibers?
That's a good question. Yes, it is, and it's being test validated by prominent universities in Germany and USA.
Okay. Does the GENOA 3D printing or 3DP software have does it use a validated database of materials for composites and metals?
Yes, that's correct. We do have validated materials. The software comes with 10 for thermoplastics, thermoset elastomers. We just showed Ultem 1010 and ABS AS4. I'm sorry, it comes with 11 validated materials with references that are our own publications and test data references. For metals, we do have validations for Inconel, titanium, and pH steel.
Okay. Excellent. Do we have any additional questions from anyone, or are these answering the questions that anyone had? All right. Well, I think that kind of closes everything up. But I do want to thank everyone for joining us on this TRX webinar. I want to thank Cody Godinez for the presentation and everyone at AlphaSTAR for putting this together with us at America Makes. I want to let everyone know that if you do have additional questions or would like to take a little bit more in-depth conversation offline with our friends at AlphaSTAR, you can see the information email there on this slide. Once again, thanks to everybody. There will be a post-webinar survey going out to everyone. We really do appreciate all the feedback that we get about these webinars, and we always are looking for ways to improve. We'd like to hear what you've thought about this. Also, anybody that's on the call that works in an environment where you feel you have information that maybe you'd be willing to share through a webinar series such as this, please don't hesitate to reach out to us at America Makes to be considered for one of these webinars, and we really look forward to expanding the series to include anyone that has something interesting for the broader community of additive manufacturing. So that concludes our presentation today. Thank you again, Cody. Thanks everybody for joining, and we will sign off here. Talk to you next time. Thanks.
Thank you.